Hello everyone. Automotive engineering is a field that requires a variety of disciplines. Curve fitting is a very useful tool when systematically analyzing test data. This video is the first part of curve fitting using the least squares regression, which is widely used in numerical analysis. I will explain how to formulate the least squares regression theory for curve fitting and how apply formulated equations to practical example of system equations like linear functions and polynomial functions. I will explain the introduction, the principle of the least squares regression, formulation of the mathematical expressions, and derivation of matrix expressions. Finally, I will explain the practical examples of which system equations are linear functions and polynomial functions. Among curve fittings by system function type, exponential functions, Fourier series, nonlinear functions, weighting functions that can reflect the importance of each data, and data selection that can reduce overall errors will be explained in the next video. Let's take the quiz. Which of the following system functions does not have a linear form? Please choose one of the four options here. Number 1 is a quadratic function, number 3 is a trigonometric function, number 3 is an exponential function, and number 4 is a function whose coefficient is within the augment of the exponential function. What is the purpose of curve fitting? For example, let's consider that we are given four data sets as shown in the table on the left. Sometimes we know the governing equations of the system this data represents, and sometimes we don't. Our goal is to analyze these four pieces of data to find a system function that passes through all the points as closely and smoothly as possible from the relationship between x and y, and then find the y value for any x. Because the governing equations may or may not be known, from now on we will use the term system equation instead of the governing equation. If our system is a simple vibration system with one degree of freedom consisting of a mass, a spring, and a damper, or if the governing equation is already known even though the system is complex, the known governing equation can be used as the system function. However, if we do not know the governing equations of the system, we must correctly select the system equation that best represents the data to properly perform curve fitting. For example, if you have four pieces of data as shown in the picture, you need to think about which function will best represent those four pieces of data. You must decide on a system function by considering whether a linear function, a polynomial function, a logarithmic function, an exponential function, or other functions are good. Let's consider again the purpose of curve fitting. For example, consider the simple case of measuring the displacement as shown in the figure. Let us assume that we have obtained data measuring four forces corresponding to four displacements. Is there a way to calculate from these four pieces of data what the force is in any other arbitrary displacement, say x5 or x6? We already know that the relationship between springs and forces is expressed in equation 1. However, we don't know the exact value of k. By calculating the coefficient value of the system equation, k, from these four data, the system equation 1 can be obtained. Once the system equation is obtained, the load for any displacement x value we want to know can be found for all displacements using the system equation 1. The purpose of curve fitting is to obtain the coefficient of the system equation from the given data, and from this, to obtain the value of the dependent variable for any independent variable. Of course, a prerequisite for curve fitting is that the system function is known or selected. There are two ways to obtain the system equation. The first way to find a system equation is to find a function that passes through all data sets accurately and smoothly. This method is used when the governing equations of the system are not known and the data are believed to be relatively accurate. The second way is to find a function that passes most closely and smoothly through all data sets. This method is used when the governing equations of the system are known or when the data contains errors and is therefore relatively inaccurate. Since most problems in engineering involve knowing the system's governing equations, we will explain the second method first. First, let's see what problems arise if we get a function that passes all the data exactly in the spring system shown in the figure. Given four pieces of data as shown in the figure, let's assume that we have found a function that passes exactly through all four pieces of data. The problem with this method is that it does not take into account the existence of measurement error in all measurements. We know that when we pull on a spring, it changes linearly according to Hooke's law, as shown in equation 1. If you ignore measurement errors and accurately connect the measured data, you can obtain a curve like the one in the figure. This result does not conform to our physics knowledge. If arbitrary displacement x5 and x6 values are calculated based on the equation obtained in this way, a particularly large error occurs in the case of x6. The second method of curve fitting is to find a function of a straight line that closely passes through all the data, since we know that Hooke's law is a linear function that varies along a straight line. When four pieces of data are given as shown in the figure, the goal is to find a function that does not pass through all four pieces of data exactly, but passes as close as possible. This method acknowledges that there are measurement errors in all measurements and finds a system function that minimizes these errors. In this case, the system function can be expressed as equation 1 applying Hooke's law. The task is to find the equation of a straight line that passes through all the points as close as possible, which is to find the k value of equation 1. This result is consistent with our physics knowledge. If we obtain arbitrary displacement x5 and x6 values based on the equation obtained in this way, we can obtain the force F corresponding to each value of displacement x relatively with accuracy. The system function that passes through the given data as closely as possible can be obtained by I in simple cases. As shown here, try to display several red lines, blue lines, and green lines, and so on. Finally, use your eyes to select the line that passes through all the data closest to you. Find the slope of this line, and this value becomes the k. However, there may be a more accurate k than the k obtained by I. For this reason, it is necessary to theoretically find a system equation that passes through the given data as closely as possible. There are two theoretical methods. The first one, which is explained in the video here, is the least squares regression, which finds the coefficients of the system function so that the sum of the squares of the errors between the values obtained from the system function and the data is the minimum. The second method is to minimize the maximum error between the values calculated from the system function and the data. Among these, curve fitting by least squares regression is widely used and is what will be explained in this video. Curve fitting using the least squares regression has different calculation principles depending on whether the system function is linear or nonlinear. A linear function can be expressed as equation 3. To help you understand, examples of linear form functions and nonlinear form functions are shown in equations 4 to 13. Simply put, a linear function is a function in which the coefficient c is not contained within augment of the function, and a nonlinear function is a function in which the coefficient c is contained within the augment of the function. If you look at the linear functions from equation 4 to equation 8, the inside of the functions of x, x squared, sine x, cosine x, and 2x, that is, the augments, do not contain coefficients. On the other hand, looking at the nonlinear functions, equations 9 to 13, e to the c2, sum of c2x and c3x to the c4, c2x to the c3, sine c2x, cosine c4x, sum of 1 and c2x to the c3 are included inside the function, that is, in the augment. Curve fitting using the least squares regression can only be used for functions that have a linear form. To use the least squares regression for a nonlinear equation, the nonlinear equation must first be converted to a linear form. The form of equation 9 becomes linear in a logarithmic coordinate system if the natural logarithm is taken on both sides, so the least squares regression can be used. The remaining nonlinear equations are curve fitted using an iteration method using Taylor series. We call this process nonlinear least squares regression. Let's learn about the principle of least squares in the case of straight line. If the system function is a linear function expressed in equation 17, let us learn the principle of the least squares regression. Let's say the system equation is equation 17, y equal ax plus b. Now, let's analyze xi and yi among several measurement data. Because the measured data contains errors, it does not conform to the system equation line and deviates from it. When a vertical line is drawn from xi, the y-coordinate value of the system equation diagram is axi plus b, as shown in equation 15. Meanwhile, the measurement data at the x-coordinate xi is yi. As shown in equation 16, yi deviates from the y value of the system equation by Ri. This amount of deviation is called residual and is expressed as Ri. The residual value of each data set can be expressed as equation 16. The least squares regression is to find the coefficient of the system equation that minimizes the sum of the squares of the residual values Ri of all data, as shown in equation 14. Before deriving the formula for least squares regression, let's make sure we remember something about the coefficients of the system equation. No matter what the system function is, the coefficients of the system equation we want to find are unknown variables, and the data are constants because they are all known values. For example, if the system function is a linear function expressed in equation 17 and there are 4 data sets as shown in the table on the left, you can substitute them into the system equation to obtain an expression for each data as shown in equation 18. What we want to find are the variables a and b, so these two coefficients a and b are unknowns, and other numbers such as x1, 2, 3, 4, and y1, 2, 3, 4 are all known values, so they are constants. If this relationship is explained using equation 16 obtained earlier, residual Ri is the dependent variable, a and b are the coefficients of the system equation and are unknowns, so they are variables, and xi and yi are constants because they are already known data values. Let's learn about the partial derivative of the residual expressed in equation 16, calculated using the system equation. If equation 16 is partially differentiated with respect to coefficient a, coefficient b is a variable, but since it is partially differentiated with respect to a, it is treated as a constant and becomes 0, and yi becomes 0 because it is a constant as data. Therefore, this result becomes xi as shown in equation 19. If equation 16 is partially differentiated with respect to coefficient b, coefficient a is a variable, but since it is partially differentiated with respect to b, it is treated as a constant and becomes 0, and yi becomes 0 because it is a constant as data. Therefore, this result becomes 1 as shown in equation 20. By the same principle, if you calculate partial derivative of the square of the residual expressed in equation 21 with respect to variable a, you can obtain the result of equation 22, and if you calculate partial derivative with respect to variable b, you can obtain equation 23. Now that we know how to do partial differentiation, let's derive equations for curve fitting using the least squares regression when the system equation is the first order function. Let's formulate a theoretical equation for the least squares regression. Let us denote the sum of the squares of all residuals as r. Substituting the Ri in equation 16 into equation 14 gives equation 24. As already explained in equation 16, yi and xi are constant values because they are measured values. On the other hand, because a and b are coefficients of a system equation that has not yet been determined, they become variables rather than constant values. Therefore, since r is determined according to a and b are independent variables of r and Ri is the dependent variable. The necessary condition for the minimum value of r in equation 24 is that the partial derivatives of r with respect to a and b are each 0. This can be expressed as equation 25 and equation 26. Continuing, the partial derivatives of residual are with respect to coefficients a and b expressed in equations 25 and 26 are all 0. By solving and organizing the sigma function of equation 25 and equation 26, equation 27 and equation 28 can be obtained. Since a and b are unknowns and there are two equations, you can find the coefficient values of the system function a and b by solving these two equations. Equations 27 and 28 are called normal equations. Now that we have derived the principles and basic equations of the least squares regression, let's take a look at how it is used through various examples. Let's look at the case where the system function is a linear function and passes through the origin. If the system function is a linear function and passes through the origin, the intercept value of the system function is 0, so the b value is 0. Therefore, the system function becomes the equation of a straight line with one coefficient, as shown in equation 29. Let's find the coefficient a using the least squares regression. Let's consider the case where there are 5 measurement data. If you make equation by substituting each data into the system function equation 29, it can be expressed as 5 equations, as shown in equation 30. If the measured data values are as shown in the table, they appear as blue dots when displayed in a scatter plot. When the system function passes through the origin, b in equations 25 and 27 obtained above is 0, so equation 27 can be expressed as equation 31. From this, the coefficient a of the system function can be obtained as equation 32. If you actually calculate a, you can get the value of 1.979 as shown in equation 33. The yellow line on the graph represents the linear function that most closely passes through all measured data. This time, when the system function is a linear function and does not pass through the origin, we will find the coefficients a and b using the least squares regression. As before, let us consider the case where there are 5 measurement data. If you formulate a residual expression by substituting each data into the system equation 17, it can be expressed in 5 equations, as shown in equation 34. If the measured data values are as shown in the table, they appear as blue dots when displayed in a scatter plot. If the system function is a general linear function, the coefficient of the system equation can be obtained from equations 27 and 28 obtained previously. If you calculate each term in equation 27 and equation 28, you can get the result of equation 35, and by substituting these values into equation 27 and equation 28, you can get equation 36 and equation 37, which are normal equations. From these two equations, calculating the slope a and intercept b, we can get the result in equation 38. Therefore, the system function can be expressed as equation 39. If equation 39 is visualized, it becomes the orange line in the figure, representing the first-order function that most closely passes through all measured data. A system function is a function that represents the relationship between the input and output of a system. System function depends on how you define the system. For example, the figure here represents a simple mechanism consisting of a spring and a fixture. Let's look at how to set up the system function in two cases, the lowercase x-coordinate system and the uppercase x-coordinate system. Let's first look at the measurement system for coordinates, denoted by the lowercase letter x. Figure A indicates a state in which no weight is hanging on the spring. In this state, the displacement x, shown in lowercase, is 0. In figure B, the weight of the fixture is added, resulting in a displacement of the lowercase letter x 0. In figure C, one weight is added to the system, resulting in a displacement of a lowercase letter x1. In figure D, 2 weights are added to the system, causing a displacement of a lowercase letter x2. In figure E, 3 weights are added to the system, causing a displacement of a lowercase letter x3. In the coordinate system denoted by a capital X, the displacement containing the fixture weight is defined as 0. Therefore, in figure C, 1 weight is added to the system, resulting in a displacement of capital letter x1. In figure D, 2 weights are added to the system, resulting in a displacement of capital letter x2. In figure E, 3 weights are added to the system, resulting in a displacement of capital letter x3. The data we measured is as shown in the lower left table for the lowercase x coordinate system. They can be represented visually. As shown in figures C, D, and E, the displacement due to the addition of weight can be represented by the lowercase letters x1, 2, and 3. We don't know the fixture weight and the displacement of x0. For the uppercase x coordinate system, our measured data is as shown in the lower right table. As shown in figures C, D, and E, the displacement due to the addition of weight can be represented by capital letters x1, 2, and 3. Since the vertical axis coordinate including the fixture weight is defined as 0, the graph passes through the origin. Let's find out how the system functions differ between the lowercase x coordinate system and the uppercase x coordinate system. If you graph the system equation of the lowercase x coordinate system, it will look like f in the bottom left. In this case, the system function can be expressed as the equation f of a straight line intersecting x0, which corresponds to the weight of the fixture and has a slope c and an intercept x0 that intersects the x-axis. In this equation, c and x0 are the coefficient values we need to find out with the curve fitting method. In contrast, the uppercase it can be expressed in an uppercase x coordinate system, and the graph passes through the origin because the vertical axis coordinate where the fixture weight is added is 0. Therefore, the vertical intercept lowercase letter x0 disappears, and it can be expressed as g, an equation with only the slope c. In this equation, c is the coefficient value to be found by curve fitting method. For the lowercase x coordinate system, the system function does not pass through the origin because there is an intercept x0 of the x-axis corresponding to the weight of the fixture, as shown in equation f. Therefore, the slope c value and intercept x0 value of the straight line that most closely passes through the three measured data must be obtained using the curve fitting method. On the other hand, in the case of the uppercase x coordinate system, there is no x-intercept because the system function expression g passes through the origin. Therefore, you only need to find the slope c value of the straight line that most closely passes through the three pieces of measured data using the curve fitting method. Here, one thing to note is that although using equation g makes the calculation simpler, if the measurement error is severe, there is a possibility that the slope c may be calculated incorrectly. Let's find out why. When using the equation g that passes through the origin, if the measurement error is small, the slope c of a straight line passing closely through the three measurement points can be obtained by curve fitting using the least squares regression as shown in figure H. However, when the error in weight measurement becomes relatively large, as shown in figure I, or the error in displacement measurement becomes relatively large, as shown in figure J, an error occurs in which the straight line obtained by the least squares regression moves away from the measurement point compared to figure H. This is because equation g passing through the origin was used as a system equation. In this case, the slope of the system equation obtained by the least squares regression contains a significant error. Let's find out how to improve this. The method described here can be used when the displacement measurement or weight measurement is incorrect and the same amount of error is included in all three measurements. Even if it is theoretically true that the system function passes through the origin, measurement error must be considered, so do not use equation j, but use equation k to obtain the intercept value x0 and slope c with respect to the x-axis. In theory, the equation of a straight line must pass through the origin, so x0 can be considered an error. On the other hand, since the same amount of error is included in the three measurements, the slope c can be considered relatively error-free, as shown in figure K. Therefore, measurement error can be eliminated by using the equation L, which ignores the intercept x0 in the equation K obtained by the least squares regression. Equation L is shown as a blue straight line in figure L. If the system function is a quadratic function, let's learn the principle of least squares regression. Let's say the system function is the quadratic function represented by the blue line in equation 42, y equal ax squared plus bx plus c. Let's analyze xi and yi among several measurement data. Because the measured data contains errors, it does not conform to the system function line and deviates from it. When a vertical line is drawn at xi, the y-coordinate value of the system function curve is as shown in equation 40, axi squared plus bxi plus c. Meanwhile, at the x-coordinate xi, the measured data is yi and deviates from the y value of the system equation by our I in equation 41. The amount that deviates like this is called residual and is expressed as our I. The least squares regression is to find the coefficient value of the system equation that minimizes the sum of the squares of our I, which is the residual value of all data, as shown in equation 14. To find the coefficients to make the residuals equal to 0, we have to calculate partial derivative of residuals with respect to each coefficient. Let us denote the sum of the squares of all the residuals as our substituting our I in equation 41 into equation 14 gives equation 43. In equation 43, yi and xi are measured values and therefore constant values. On the other hand, a, b, and c are coefficients of a system equation that has not yet been determined, so they are variables rather than constant values. Therefore, because r is determined by a, b, and c, the coefficients of system equation a, b, and c are independent variables of r. The necessary condition for the r in equation 43 to be minimum is that the partial derivatives of r with respect to a, b, and c are each 0. This can be expressed in three equations, equations 44, 45, and 46. Now, we can formulate the equations for least squares regression. By solving and rearranging the sigma functions of equation 44, equation 45, and equation 46 derived earlier, equation 47, equation 48, and equation 49 can be obtained. Since a, b, and c are unknowns and there are three equations, the coefficient values a, b, and c of the system function can be obtained by solving these three equations. Equation 47, equation 48, and equation 49 are called normal equations. When the system function is a quadratic function, we have derived the principal and basic equation of the least squares regression, so let's take a look at how it is used through various examples. Let us consider the case where the system function is a general quadratic function that does not pass through the origin and there are 5 measurement data. If the system function is a quadratic function and does not pass through the origin, the system equation can be expressed as equation 42. Let's find the coefficients a, b, and c using the least squares regression. Let's consider the case where there are 5 measurement data. If you formulate an expression by substituting each of the 5 data into the system equation 42, it can be expressed as 5 equations in equation 50, including y1, y2, y3, y4, and y5. If the measured data values are as shown in the table, they appear as blue dots when displayed in a scatter plot. Using the normal equations 47, 48, and 49 obtained earlier, we can find the coefficients a, b, and c of the system equation. First, if you calculate the value of each term included in the normal equations using the data in the table, we get n, sigma xi squared, sigma xi cubed, sigma xi to the 4, sigma yi, sigma xi yi, and sigma xi squared yi in equation 51. By substituting these values into equations 47, 48, and 49, we can obtain the normal equations 52, 53, and 54. From these normal equations, the coefficient values of a, b, and c of the system function can be obtained as shown in equation 55. From this calculation result, the system function can be expressed as equation 56. If equation 56 is visualized, it becomes the orange line in the figure, which represents the quadratic function that most closely passes through all measured data. Summarizing what has been explained so far, when the system function is a polynomial with degree p, equations for curve fitting can be derived. A general polynomial of order p can be expressed as equation 57. Here, if p is 1, it becomes a function of a straight line. From equation 57, we can see that the number of parameters we need to find is p plus 1. Therefore, we can see that the number of data for curve fitting must be larger than m, which is the total number of polynomial coefficients. The residual expression for the polynomial function can be expressed as equation 58. Equation 59 can be obtained by calculating partial derivative of each residual r for m parameters. By calculating and rearranging equation 59, the normal equation can be obtained, and from this, m parameter values can be obtained to complete the system equation. In curve fitting, normal equations can be expressed in matrix form. For example, if the system function is a polynomial with degree p, the normal equation can be expressed as equation 60 by referring to the 3 equations 47, 48, and 49 obtained previously. Expressing equation 60 in matrix form, equation 61 can be obtained. Equation 61 expresses the normal equation in matrix form. For example, if the system function is a quadratic function, the matrix expression of the normal equation can be expressed as equation 62 by referring to equation 61 obtained previously. By substituting the data xi and yi used in the previous example into the normal matrix equation 62, equation 63 can be obtained. By solving the matrix equation of equation 63, the result of equation 64 can be obtained. It can be seen that this result is the same as the result of equation 55 calculated previously. This time, we will express the curve-fitting calculation formula using the least squares regression for a general linear system function in matrix form. The general system equations in linear form can be expressed as equation 3, which was previously described. Equation 3 has m coefficient values, which is the number of unknowns we will calculate. As shown in the table on the left, when the number of data is n, if each data is substituted into equation 3, it can be expressed as equation 65 using the sigma function, and the total number of equations is n equal to the number of data sets. If equation 65 is solved separately, it can be expressed as equation 66. Remember that the number of unknowns is a total of m coefficients from C1 to Cm, and the number of data set is n from x1 y1 to xn yn. We have studied the principle of the least squares regression in equations 24, 25, 26, 43, 44, 45, and 46 derived earlier. The principle of the least squares regression is to find the value ck of all coefficients so that the sum of square of the error values is minimum, so this can be expressed as equation 67. If equation 66 is expanded for all n measurement data sets, it can be expressed as equation 68. In other words, to express this differently, by substituting equation 66 into equation 67 and calculating partial derivative for each coefficient from C1 to Cm, equation 68 can be obtained. Our goal is to express equation 68 in matrix form. Remember that in the expression of the equations here, the number of coefficients we need to find is m, and the number of data set is n. Equation 68 can be expressed in matrix form as shown in equation 69, in which we have the residual row vector R, the partial derivative matrix with respect to the coefficient Ci, and zero row vector. In this equation, the number of entries of the residual row vector is n, and the partial differential matrix has n rows and m columns. The right-hand side of equation 69 represents a zero row vector with n entries. M is the number of coefficients or parameters that the system equation has, and n is the number of data sets. Among each entry of the rectangular matrix of equation 69 obtained earlier, let us calculate the three colored elements. If you calculate the partial derivative by substituting the residual function, R1, expressed in equation 70, into the green matrix entry of equation 69, all terms in residual 1 that do not contain C1 are 0, so you can obtain equation 71. Next, if you calculate the partial derivative by substituting the residual function R1 expressed in equation 70 into the blue matrix entry in equation 69, all terms in the residual that do not contain C2 are 0, so you can obtain equation 72. Additionally, if you calculate the partial derivative by substituting the residual function R2 shown in equation 70 into the purple matrix entry in equation 69, all terms that do not contain C1 in residual R2 are 0, so you can obtain equation 73. As a result, if you calculate the partial derivative for the coefficient ck by substituting the general term Ri of the residual function expressed in equation 70 into the corresponding entry of equation 69, all terms that do not contain ck in residual Ri are 0, so equation 74 can be obtained. From equation 69 and equation 71 derived previously, if we substitute the result of equation 71 into equation 69, we can see that the partial derivative entry in equation 69 can be replaced with each term of the system equation. Therefore, the rectangular matrix in equation 69 can be replaced with the terms of the system equation as in equation 75, which is denoted as the F matrix. Let us replace the rectangular matrix in equation 69 with the F matrix in equation 75. By replacing the rectangular matrix of equation 69 derived earlier with the F matrix of equation 75, the result of equation 76 can be obtained. To simplify this, it can be expressed as equation 77 using the matrix symbol F. Matrix F in equation 77 was previously defined as equation 75. The next step is to expand the residual function to represent the measurement data. Since it is inconvenient to calculate if it is a row vector, it is necessary to change both the residual R vector and the zero vector, which are row vectors, to column vectors. Equation 77 obtained previously can be expressed as equation 78 using the residual row vector of equation 79 and the zero row vector of equation 80. As mentioned earlier, for computational convenience, equation 81 can be obtained by converting both sides of equation 77 into a transpose matrix. In equation 81, Ft is the transpose matrix of matrix F, so the rows and columns are swapped and can be expressed as equation 82. In AFT matrix, the number of rows is m and the number of columns is n. The number of rows represents the number of coefficients of the system equation, and the number of columns represents the number of data sets. Since our t and 0t in equation 81 are column vectors, they can be expressed as equation 83. Meanwhile, if the residual values of equation 66 obtained previously are expressed as a column vector, they can be expressed as equation 84 using the measured value yi, xi, and yi in equation 84 represent measured values. The number of residual column vector entries is equal to the number of measurement data sets, and m of the sigma function represents the total number of unknown parameters ci. By substituting our t expressed in equation 84 into equation 81 can be made into an expression that includes measurement data. By substituting the column vector rt from equation 84 obtained previously into equation 83, equation 85 can be obtained. Continuing to rearrange the fty term in equation 85 by moving it to the zero column vector, equation 86 can be obtained. Ck in equation 86 is the unknown parameter we need to find, that is, the value of the coefficients. The sigma function in equation 86 can be separated into a column vector of coefficients c and fx matrix consisting of each term in the system equation. If we separate and organize the coefficient values of the sigma function in equation 86 obtained earlier, they can be expressed in a matrix equation as in equation 87. The column vector c in equation 87 is defined as equation 88. By substituting the matrix equation in equation 87 into equation 86, we can obtain equation 89, which is the final matrix equation we want to obtain and the normal equation to be used for curve fitting using the least squares regression. We can find the unknown c column vector by solving equation 89. Solve the same problem where the system equation we solved in the previous example is a quadratic function using the matrix equation just derived. From system function equation 90, we can find equations f1x, f2x, and f3x as shown in equation 91. Each term in matrix normal equation 89 can be calculated using the data in the table in equation 91. The coefficients we need to find are c1, c2, and c3 as shown in equation 92. The column vector y can be obtained as 93 by substituting the measurement value y from the table. The F matrix can be obtained as equation 94 by substituting the x data from the table into equation 91. Obtaining the transpose matrix from the F matrix in equation 94 results in Ft expressed in equation 95. By substituting equations 92, 93, 94, and 95 calculated above into equation 89 and solving, the coefficients of equation 90, C1, C2, and C3 can be obtained, which are consistent with the results of equation 56 obtained previously. Here we have summary. The purpose of curve fitting are firstly, when you know the governing equations, to find the coefficients of the system function that pass as closely as possible through all the points in the given data, and then find the values of the dependent variable for any independent variable. Secondly, if you do not know the governing equations, to assume a system equation that best represents the distribution shape of all points in the given data, then to calculate the coefficients of the system equation, and finally to obtain the dependent variable value for an arbitrary independent variable. Principle of curve fitting using the least squares regression is to find the coefficients of the system equation that produce the smallest sum of the residual squares, which is the difference between the value of the system equation and the measured data. If the calculation formula of the least squares regression is expressed as a matrix equation, the entire calculation can be easily performed. Let's find out the answers to the quiz. What is the system equation which is not linear? The correct answer is number 4. Since function 1 is linear with with respect to coefficients C1 and C2, the least squares regression can be applied directly. Function 2 is linear because the coefficients C1 and C2 are outside the trigonometric function, and the least squares regression can be applied directly. Likewise in function 3, since the coefficient C1 is outside the exponential function, the least squares regression is possible. Function 4 is nonlinear because the coefficients C1 and C2 appear in multiplicative form, and C3 is within the augment of exponential function. Therefore, the nonlinear least squares regression must be applied. If you watch the previous videos, you can easily understand upcoming videos. In video number E0063 of High Performance Driving Volume 4, which is Principle and Theory Part 4, I explained left foot braking and friction circle, straight ahead and turning for front-wheel drive and rear-wheel drive vehicles, driving at the limit and friction circle, traditional and modern driving routes, and trail braking. Recently, in video number E0064 of High Performance Driving Volume 5, which is Principle and Theory Part 5, I explained the importance of vehicle balance, understanding the mechanism of the vehicle, how to feel the vehicle, and the elements of high-performance driving. The next video is the second video of curve fitting using the least squares regression and will explain the curve fitting of the Fourier series, weighting function, and the selection of data. Please hit the thumbs up and catch the brand new videos by free subscription, so what are you waiting for? See you at next videos. Goodbye, guys.